How you doing, Raylan?
I'm good, how are you?
Can you hear me?
Yes.
Okay, great, great. Hey, Zach. Gotta get fixed. All right, guys, let's get started. Let's get started. If you can turn on your camera so that I can see you, because it works so much better when I can see your faces. I know how much time you need and stuff like that. Let's stretch. Stand up, stretch. It's Friday. It's Friday. Stand up, stretch wherever you're at. Just stand up. Oh. You're going to be listening to my horrible voice. You're going to be listening to my horrible voice here for the next hour and 15 minutes. Okay, sit back down, sit back down. We have a what? We have a what next Wednesday? Quest. Okay, it'll be part WebAssign. It'll be part WebAssign. And then the more difficult part, the proofs and things like that, will be handwritten. And so what I'm going to do is on Canvas, I'm going to open up an assignment at the same time the WebAssign opens. And you'll have about half the class period to do both pieces. But ultimately, you're going to have to be able to get me your solutions, okay? And the easiest way to do that is with your phone. Your phone has a scanning app, okay? Whether you're Android or iPhone, and it makes it really pretty simple. And so I want you guys playing with that before next Wednesday. And so what I'm going to do now is I'm going to go share my screen and show you what I put up for you guys to help you with that.
Hey, Dr. Warren, Patrick wanted me to tell you that he's not feeling too good.
Oh, no.
He wanted me to let you know.
Hopefully it's from drinking. You see, I'm not sure I'll be able to. I'm not sure which one it is. Maybe I'll try this Are you guys getting this at all? Are you seeing these announcements? Are you seeing it?
Yes.
Okay. So I have this announcement here. You know, I didn't realize that every time, let me run up here again. I didn't realize that every time I put up an announcement, you guys got some notification. I can't imagine how many stinking notifications you get every day from professors putting stuff up. I just like, I would be overwhelmed. I would be overwhelmed. Now, when I add to it, do you also get a notification or does it not notify you?
No.
Yay, that's what I want. You know where things are at. If it's really important, I'll send you an email. But here, this kind of explains, like if you're an Apple user, how to do it. If you're an Android user, how to do
Hi,
it.
my name is City and welcome back to the channel where we make educational technology easy for you.
And then, if you're an Apple user, there's this guy.
Hi, this is Gary with MacMost.com. Let me show you how you can.
With the Android, you have to download. Most of you have it, the Google Drive app. You have to have the Google Drive app. But I want you guys playing with this because this will be huge. This will be huge for you guys all semester to be able to do this, not just for my class, but for any class. Sorry, it sounds like a huge echo. There's this pretty easy to use plotting package that's free on the web. A lot of what you guys are going to be struggling within this class, even though you live in a three-dimensional world, you haven't done math in a three-dimensional world. And so this plotting app is really kind of nice to help you guys. It's free. And so it just links up. But like, for example, I can just grab this, and then I can look right underneath it. Or I can see it from any angle I want. And so this is really a pretty nice app for you guys to plot vectors and other things. I put up this.
All right, guys, I'm trying to make a recording.
Clearly, I lost my coffee.
I'm gonna plot vectors with that software we were playing around with in my first section on spin things around so that we can let's, I guess, get them in the game. So let's.
You can go through and listen, but essentially this is an easy way to plot.
This is their three-dimensional space.
So now I'm going to add a second vector.
And look down the shadow that would be cast onto the blue vector. I want to get that vector. I want to get what we're calling a parallel. It's parallel to B.
Okay.
Parallel to B.
Stop. I can't stand hearing my voice. So there's a parallel. There's a parallel. And again, you guys can watch the video. And then ultimately, I end up showing you how to put in your perpendicular vector. And then you can just spin it around.
We've got here is we plotted.
And so my idea is that seeing it helps it really register. When you see it and you can move it, it helps it really, really register. Oh, let me share again. Sorry. There was one other thing I wanted to point out that I don't think you guys know about yet, because I haven't really sent an announcement. In files, there's a section called Very Rough Notes. And, oh, I didn't put up, okay, I must have put them up in the first class, but not the second. But this is where I'm going to put notes for 12.1, 12.2, and 12.3. And like, here's just some rough notes. Here's just some rough notes related to some of the stuff that we've been doing in class. Some of the stuff we didn't do, but some of the stuff we did do. And I'll put up notes for all of the sections as we're heading into the quest in that directory. Okay. All right, stand up again, stand up again. I can already tell you need it. Stand up again. I know you need this. You know you need this. Okay, let's sing the fight song. Let's sing the fight song. Madison, James Madison. We are the Dukes of JMU. You can't hear anybody but me. Madison, I'm an alum. Madison, we are the Dukes of JMU. I don't know the rest of the song. Fight for honor, fight for something else. We're going to survive COVID. Madison, James Madison. Okay, sit back down. You've had enough of me. You had enough of me. But you should be awake. You should be awake. Okay, today we're going to make a long proof. You're like, oh, that's what I wanted to hear, Dr. Warren. Today we're going to make a long proof. But we're not going to start with it. We're going to get your brains going. Part of my quest will be true and false questions. Who's had me as a teacher before? Who's had me as a teacher before? Those are the worst. Those are the worst. On somebody's final one time, at the end, I just take the quarter to it before I gave it to them. I'm like, use the quarter instead of guessing, because you'll miss more. You'll get more points by using the quarter. Okay? You have to have your definitions really down cold to get my true and falses. You should have now about 26 flashcards. That first page of flashcards, somebody said there was one cross product. That's not needed for Wednesday. But you should have those first page of flashcards, those 26 flashcards, pretty much down by next Wednesday. Now, something that I could do over here, and let me show you how easy it is to trick you. I could say, true or false, the definition of A dot B is the norm of A times the norm of B times the cosine of theta. That's something I could ask. Is the definition of A dot B the norm of A times the norm of B times the cosine of theta? And what would the answer be? True or false?
False.
False. That's not the definition. That's something we proved with the law of cosines. The definition in this class is what? The definition in this class, I'm helping you get ready for Wednesday. The definition is what, guys?
A1 times B1
Perfect. A1 times B1
plus A2 times B2 plus A3 times B3.
That's the definition. Perfect, perfect. That's awesome, Raylan. Thanks. You guys, now, everybody says Calc 3 is so hard. It's not so hard, it's just a lot of computation. Everything is tripled from what it was in Calc 1 and Calc 2. I don't think conceptually it's any harder than Calc 1. I actually think Calc 1 is the hardest material. Okay, here's two vectors. Can you guys see the vectors? I got to write bigger. This is the vector A, this is the vector B. I want you guys draw yourself a set of vectors, and I want you to draw A parallel and A perpendicular. I want you to draw the vectors A parallel to B and A perpendicular to B. Now hold them up to the screen when you're done. Hold them up to the screen so I can see what you've drawn. Hold them up to the screen so I can see. I'm coming to the front of the room where you guys are at. Yeah, that looks great. That looks awesome. Some of you didn't draw the parallel. Okay. Luke, I'm not quite sure what we got there. It should be at a right angle. Maybe you're going, okay, good. Almost everybody's got it. If I'm looking at it, if I want to draw a parallel, I drop an altitude. I drop a 90 degree. I go down so that we're perpendicular here. Okay, and this vector right here. This vector right here is a parallel. So we'll just use those double lines, and then we'll make it bold, which is kind of like this thing. And then this is clearly A perpendicular. That's clearly A perpendicular. Now, without looking at your notes, I want you to write down the flashcard that you've got in your brain, if I gave you two specific vectors, like I will next Wednesday, if I gave you two specific vectors and asked you to calculate a parallel, what flashcard would you not want to be struggling to get? Write it down, I'm helping you. Without looking at your notes, what flashcard would you want to immediately have? Write it down. Okay, now I think some of you are going to be less likely to want to share. Hold it up to the screen. What you got? Some of you aren't even, what you got? This is accountability. What do you got for me? Oh yeah, Mason. Look at Mason. Emily, I can't quite see it, Emily. Sorry. Emily, I'm believing you're right. Greer, could you hold your up a little bit more? Oh, you poor guys, I can't believe you have to look at I hope I'm not as blurry as a lot of your stuff. Okay, there's a lot of wonderful things. What is the right answer, guys? A dot B.
Over the norm of B.
This is the easiest way to calculate it. Over the norm of B squared. Now this is a scalar. Does this make sense? This is a scalar. The dot product's a scalar, the norm's a scalar. A scalar divided by scalar is a scalar. I need the vector. What else do I need? What else do I need there?
The vector B.
The vector B. There's the flashcard. Now I've got to ask, if I give you two vectors with 6 real numbers, is it that hard to calculate A dot B? Or the norm of B squared, you don't even need the square root. And then you multiply it times B. I assigned a bunch of homework where you're doing that. Okay, there's another thing that's important, and again, you won't know why until later. We also want to talk about the length of the vector A parallel. We also want to talk about the length of the vector A, or the component. I can't quite get away with length. It's more like displacement. There's a sign in it. I want to talk about what, I don't think if I yell, that means you guys are going to learn better. Okay, what can I do? Okay, I'm going to go Uncle Janice. I had an uncle in Kentucky, and I was so unathletic, I drove him nuts. His son was a professional golfer, and then he took me out golfing. But he had the deepest southern drawl I've ever heard. He would go, Paul, listen to me, boy. I don't think I've ever seen another human being swing a golf club like that. You got to be the worst golfer I've ever met. Now, if I've got a vector here, and I want to talk about the component of the vector. I'm talking about what number would I have to multiply times the unit vector in the B direction to get a parallel. I can't keep doing it. I still have scars. Okay. What would I have to multiply times the unit vector in the B direction to get a parallel? And the flashcard comes directly from this. This is not a unit vector. This is not the unit vector. If I steal one of these guys, then it is a unit vector. A vector divided by its norm is a, I'll keep on. A vector divided by its norm is a,
Vector.
what kind of vector?
Unit. Vector.
Everybody put your finger down on the space bar. We're going to blow the speakers. A vector divided by its norm is a...
Unit vector.
Okay, not loud enough. I didn't hear any feedback. I want feedback. A vector divided by its norm is a... Unit vector. Awesome. This is the component. Of a parallel. Now, They won't, of course, let us get away with writing that down. They've got to introduce some symbols that makes it look far more complicated. They'll write this down. They'll use COMP to stand for, guess what? Guess what? If you had to guess, what would you guess it would be? Component. Then they put the vector A here. And so it's the component of A. And then they put a little b vector subscript. And so the component of A in the B direction is just A dot B over the norm of B. A dot B over the norm of B. So you actually have to deal with the square root. You actually have to deal with the square root. And then they give you this thing. They have this other symbol that looks like this. I mean, the nice thing is when you go home for Thanksgiving, like you show your parents your notes, they'll be like, whoa, you're learning some really complicated stuff. But you don't have to tell them, this just means a parallel. This just means a parallel. We say it's the projection, say that.
Projection.
The projection of A onto B. Say that again.
The projection of A onto B.
Onto B, yeah. So let me just, I'm afraid okay, I'm now turning off the lights. I'm not sure here. Hold on, I'm turning on my flashlight. This is not going to work at all, is it? So I've got this vector. I'm not sure this will work. I've got to try to hold it with one hand. But if I would shine my light, this isn't working. Well, maybe. If I shine my light right above my blue vector and look at the shadow that's cast onto the green vector, it ends perpendicular. If I shine a light right there, my hand's in the way. I know this is not doing anything for you. The shadow goes right there. I need a better flashlight, something that's brighter. That's why they call it projection. That's why they call it projection. I imagine the sun is right here. Where would the shadow be? Where would the shadow be? Where would the shadow? If the sun's right above it, where's the shadow going to be? It's going to run right here. It's going to run right here. We're at noon, and we call this the projection vector. But we're just going to call it in this class a parallel. But in the book or in any of your other classes, when they're talking about the projection of one vector onto another vector, this is what they're talking about. This is what they're talking about. Okay. Here's a question. Let's see what's in your gray matter. What are the three most important vectors in this class? What are the three most important vectors in this class? I, J, and K. Write down the component forms of I, J, and K. What's in your gray matter? Write down the component forms of I, J, and K. Okay, hold up what you got. Hold up accountability. What do you got for me? What do you got for me? What are the component forms of these? Oh yeah, baby. Dead on. Mason, you own it. Yeah, Robert, awesome. Good job, guys. Okay, so I'm looking at it. What's the component form? What's the component form of I? What's the component form of I? Hold down that space bar and just call it out.
1, 0, 0.
1, 0, 0. And then the rest of them, 0, 1, 0, and 0, 0, 1. Okay, so now I got this, and this is kind of, I wish it didn't have quite, I'm thinking of this as being I, I'm thinking of this as being I, this would be
J.
K, and then this would be
J.
J. This points in the X direction. This points in the X direction. We go out one, we got the arrow there. This is my I vector. This is my J, and this is my K. So I've got these vectors like this. I'm going to draw them here. Here's my z-axis, my y, z, x. That vector that I just drew would be, I. This vector would be
K.
K, and this vector is then J. Now imagine that I did the same thing. I took a light and just shined the light right above my Z. How much shadow would fall on I or J? If I'm holding a light source right above it, how much shadow would fall on I or J? You're like, well, Dr. Warren, this is dimensionless. If you're holding a light source here, this is straight above it. You're not going to get any shadow. You're not going to get any shadow on I or J. Now let's see if the geometry of the dot product captures that. At your seats, do I dot J. At your seats, calculate I dot J. You just wrote down those vectors, calculate I dot J. And what do you get what scalar do you get, guys? What scalar do you get when you do I dot J? What scalar do you get when you do I dot J?
0.
0. And so we see our dot product does capture that idea of projection really well. And you guys, I'll let you do this, but I mean, you guys all, I dot K. When you're using the dot product, what do you get when you do I dot K?
0.
0. Okay, so now imagine that I've got a vector I. Well, I guess black's not the great color. I've got a vector I, and I take the vector I. Okay, and I put them right on top of each other. Right, I can even move my I up here. And I put a light source right above it. What's going to happen with the shadow? What's going to happen with the shadow? When I project I onto I, how long will that be? If you project I onto I, how long would that be? Imagine you put a light source right above the blue vector and shine it down onto the red vector. How much of the red vector would be covered? How much of the red vector would be covered? All of it. All of it. I dot I should be 1. Check it. See what you get when you do I dot I. If this idea of using the dot product for projection, see what you get when you do I dot I. And what do you get when you do I dot I? What do you get when you do I dot I, guys? What do you get?
1.
1. 1 times 1 is 1, and 0 times 0, you add them together, you get 1. Okay, now, close your eyes, close your eyes, close your eyes. Okay, I'm going to call out a dot product, and your answer is either 1 or 0. J dot J. 1. J dot K. K dot I.
0.
K dot K.
1.
I dot K.
0.
J dot J.
1.
Okay, good. Do you guys get that? Do you guys get that if they're perpendicular? Now let's imagine that I've got two other vectors. I've got these two vectors in three-dimensional space. They're numbers. They're ordered triples. What did I just say? I could say anything and it wouldn't matter. I could have said, okay, SpongeBob just took a dump, and you guys would have heard the same thing. It would have been the same. Okay, if I have two vectors in three-dimensional space, I've got these real numbers. And I'm asking, are these vectors perpendicular to each other? Does that sound like a pretty difficult question? Like, for example, I think it's probably worth doing. Give me two vectors. It's pretty open. Give me two vectors. What's your vector A? What's your vector A?
4, 1.
2, 4, 1. Give me a vector B. Give me a vector B.
5, 4, 3.
5, 4, 3. Now, I'm gonna assume I'm gonna plot them with their butt. I'm gonna assume I'm gonna plot them with their butts both at the origin. So when the butts at the origin, we call them the direction vector. The one where it's butts right at the origin, we call them the direction vector. So I would plot this 2, 4, 1. I could use that package, and I plot this 5, 4, 3, and now I ask the question, are those two vectors perpendicular to each other? And you're like, well, Dr. Warren, they're in three-dimensional space. That's hard. You're giving me these things, and you're asking, are these two vectors perpendicular to each other? Like, that's a tough question. But we derived something last time. What's A dot B equal to? I know the definition, but geometrically, what's A dot B equal to?
The norm of A times the norm of B cosine.
The norm of A times the norm of B. I don't know who's saying that, but yeah, where theta is the angle between them. Where theta is the angle between, I just need to have an extra hand. See, if we were in class, I would have you guys up here with me all the time, holding things for me. It's this angle right here. If that angle is 90 degrees, now I've got a unit circle over here. If the angle is 90 degrees, or pi over 2, what's the cosine? If the angle's 90 degrees, remember for an angle, on the unit circle, cosines the x-coordinate, sines the y-coordinate. When you're at 90 degrees, what's the cosine?
1.
0. The x-coordinate is 0, the y-coordinate's 1. So if they're at 90 degrees, if the vector A is perpendicular to B, then we get the norm of A times the norm of B times the cosine of pi over 2. The angle between them would be pi over 2, which is 0. So if you want to figure out if two vectors are perpendicular to each other, all you got to do is look at the what? All you got to do is look at the what?
Dot product.
The dot product. If the dot product's 0, then you know the two vectors are perpendicular. If it's not 0, then they're
Not perfect.
not perpendicular. Guys, I want you to understand the beauty of this. I so want you to understand this is a complicated question. You got these two vectors, these two line segments, and you're like, ooh, are they perpendicular? I can't even visualize them. Well, we come up with this algebra that says all I got to do is look at A dot B. What is A dot B? You pick the vectors. What is A dot B? You're going to have to do this next week. So what is A dot B? What number is A dot B? What number is A dot B? You're in Calc 3. What number is A dot B? I'll keep badgering you. What number is A dot B?
Yes.
So you're at 10, 33. Is 33 0? Is 33 0?
No.
No. Are these two vectors perpendicular?
No.
Hell no. In fact, it's somewhat complicated to find two vectors that are perpendicular. But the textbook does. At your seats, try to come up with two vectors that are perpendicular to each other. At your seats, try to come up, and if you pick I, J, and K, I'm going to vomit. Okay. Try to come up with two vectors other than I, J, and K that are perpendicular to each other. Try to arrive at two vectors that are perpendicular to each other. Does anybody have any? Does anybody, for sake of time, does anybody have two vectors they think are perpendicular to each other? Could they call it out? Does anybody have two vectors they think are perpendicular to each other? Jeopardy question.
0, 3, 5, 7, 0, 0.
0, 3, 5, 7, 0, 0. Who said that? Who said that? Who said that? Luke, was that you?
Yeah.
Yeah, let's give it up for Luke. Let's give it up for Luke. Thank you, Luke. I gotta ask you, Zach, are these two vectors perpendicular? Are these two vectors perpendicular? Sorry, Zach, sure. Are they perpendicular?
Yes.
Yes. Is the dot product 0? Is the dot product 0, Robert? Is the dot product 0?
Yes.
Yeah. Oh, singles. I love singles. Okay. Yeah, there's a bunch of them that'll work. There's a bunch of them that will work. We should just plot these and see that go to that graphing program. I don't have time. And just show you that they are in fact perpendicular to each other. Here's a question. Let's see how we're doing. See if you remember this. What's the definition of two vectors being parallel? What's the definition? What do you have? What do you have? So this is a theorem. A is perpendicular to B if and only if A dot B is 0. I'm not going to make you prove it. We essentially just did. But what's the definition that A is parallel to B? What's the definition that A is parallel to B? If I give you two vectors and I ask, oh, are these vectors parallel?
If B is equal to a scalar times A.
Perfect. If the vector B is equal to a scalar times A. So you guys don't have to, what were the two vectors you gave me before we had the other ones? What were the two vectors? I've immediately forgotten. What was the A before that, guys? What was the A? The vectors, what was it? 2, 4, 1? And then how about B? What was B?
5, 4, 3.
5, 4, 3. Now imagine next Wednesday I give you this and I ask, are these two vectors parallel? We know they're not perpendicular. Are these two vectors parallel? If you're an engineer, should you be able to answer that question? If you're an engineer and you're talking about putting beams, and you're like, are these two beams parallel to each other? Should you be able to answer that question? How many engineers do I have? Nick, should you be able to answer that question?
Yes, sir.
Okay. So, and I go, okay, what definition? I don't know. Well, just use the definition. If they're parallel, if they were parallel, then 5, 4, 3 would have to be equal to some real number alpha times 5, 4, 3 would have to be equal to some real number alpha times 2, 4, 1. We're just using a definition. How do you do scalar multiplication? How would you simplify alpha times 2, 4, 1? What would you do? Just distribute it in there. 2 alpha, 4 alpha, and alpha. Now let's see if this is true or false. Two vectors are equal if their components are equal. So 3 would have to be equal to, 3 would have to be equal to, 3 would have to be equal to, I'll keep going. 3 would have to be equal to alpha. But also 4 would have to be equal to 4 alpha. But this says alpha is equal to 1. But we already know alpha is equal to 3. Is this a contradiction? Is this a contradiction? Does this break a rule? Does this break a rule of mathematics? Does 3 equal 1? Would that be bad? Would that be bad? That would be bad. So there isn't a scalar. There is not a scalar that I can multiply times a to get b, which tells me then that in this case, a is not parallel to b. A is not parallel to b. But also a is not perpendicular to b. A is not perpendicular to b. And I hear you, I mean, like, I'm not going to I don't want to do that. But just think about how hard this is, guys. I just about broke the camera. Just think about how hard this is. I'm giving you arbitrary points and I'm asking you, can you come up really quickly and determine whether or not they're parallel or perpendicular? And the answer is yes. The dot product 0 tells me there, I'm hitting it again, ground stroke. Dr. Moore, you've been slamming this all day. If the dot product is 0,
It's perpendicular.
if there is no scalar, if you can't find a scalar, you find a contradiction, then they're not parallel. They're not parallel. Okay, stand up again. Stand up again. It's looking like a drug rehab. It's looking like a drug rehab. Stand up. That's when I look and see the eyes. But I can't do it in a video. I can't do it in a video. I can't see your eyes when I'm just doing a video. Stretch, stretch. You need it. You need it. Okay, look at anything that tells time. Look at anything that tells time. What time is it? What time is it?
10:24.
What time does the misery end? What time does the misery end?
11.
11. Sit back down. Sit back down. I guess I really need to ask, is this better than me getting a video? I mean, seriously, is this better? Or would you, I mean, I know it's blurry, but is it worth the effort of you guys coming and getting on Zoom?
No,
Yes, way better.
Even though it's blurry and even though it's clunky? Okay, then if it's not, let me know and I can make it. I'm still making videos just so that you can see the board, but I like it because I can see your faces. I like it because I feel like it's more like a classroom experience. And I think we'll get better at it. I'll get better at it.
Dr. I think flashlight might be on your back pocket.
I think you're right. Thanks. That would have been all day. That would have been on all day. What's worse is I'll be thinking about a theorem while I'm going to the bathroom. I'm like, sorry, I know you don't want to hear that. But then I'll like be walking around all day and my zipper will be down. And then I'll be like, you've got to be kidding me. It's such a curse to be ADD. It's such a curse to be ADD. Have you ever like been walking somewhere to get something and forgotten along the way why you were going there? And be like, what was I doing? And then to go back the other direction, and then to remember, and then to have to walk back and get it. You're like, Dr. Warren, why are you so thin? Because I forget everything. I forget everything. I'm constantly walking because I've forgotten something. Okay. I promised you a proof. No, Dr. Warren, don't do it to us. Don't do it to us. Yeah, get ready. We're going to make a proof. And you're not going to like it. You're not going to like it. It's a really important result. And it says this. And I'm going to need a brand new piece of chalk. Guys, we're going to start here. We're going to start here. And we're going to end here. We're going to start here. And we're going to end here. This is what we're going to prove. Okay, read what we have. Read what we have here. What do we have here? Theorem. The norm of A plus B. Read.
Is less than or equal to.
Is less than or equal to the
Norm of A plus the norm of B.
the norm of A plus the norm of B. This is one of the most important results in mathematics. It's used all the time. It's called the triangle inequality. It's called our triangle inequality. In one dimension, it doesn't make any sense why they call it the triangle inequality. In one dimension, it's like this. The absolute value of A plus B, the absolute value of A plus B is always less than or equal to the absolute value of A plus the absolute value of B. Now let's just make sure this makes sense. If A is 5 and B is negative 2, if A is 5 and B is negative 2, here I would get a what? Here I would get a what? 3. And on the other side, I would get a 7. And you'll have a lot of teachers in high school call this the triangle inequality. But it never makes any sense to the kids. They're like, wait, why are you calling this the triangle inequality? It's only when we jump up now to vectors that it makes sense. We'll work in the plane because it's easier to draw. Okay, draw an xy axis, and give yourself two vectors. Give yourself an A and a B. Make them direction vectors so their butts start at the origin. Give yourself an A and a B. And then what I want you to do is now I want you, like you might have to do next Wednesday, draw the vector A plus B. Draw the vector A plus B. You've given yourself a vector A and a vector B. Now draw the vector A plus B. Okay, now hold it up. Let me see what you got. I want to protect you as much as possible. Let me see if you're getting your vector sum. Seeing some good things. What you got, Rachel? Good. Nick. RJ, you got anything for me there? Okay, good. Yeah, you guys are owning this. If I'm doing the vector A plus B, I take this vector B, slide it up like this, and this is the vector A plus B. This is, and almost everybody had that. This is the vector A plus B. What does that mean? What does that symbol mean? Norm. It represents the what of the vector? The length. And so what we're saying is that if I have the length of this side and I add it to the length of this side, it's always got to be greater than or equal to the length of the other side of the triangle. If you add any two sides of a triangle, it's always got to be greater than or equal to the other side. If not, you're not going to have a triangle. If you're not, it's like the windshield wiper problem. If you want two windshields, you got two windshield wipers, and they're too short to cover the window. Are you going to have a triangle? And the answer is no. So this plus this has always got to be greater than that. And this is why it's called the triangle inequality. Okay, so now let's start the proof. And this would be the proof in physics. This would be the physics proof. That would be the proof in physics. That's what would be the proof in physics. They would say, what did I write down? What did I write down? Duh, that's what they would say, duh. Okay, yeah, you know, physically there's no way they're going to meet to make a triangle. But this is not physics, this is math. And we're going to find out it's a lot harder than duh. We're going to find out it's a lot harder than duh. Okay, so put on your proof caps, put on your proof caps, put on your proof caps, put on your proof caps. Turn on that brain, turn on that brain. Brain up. Grab your magic lasso, grab your magic lasso, grab your magic lasso. Throw your magic lasso, throw your wrap up your attention span, wrap up that little piggy, wrap it up, tie it off, tie it off. Here we go, we're setting sail. You are not going to understand our trip through Vietnam. You're not going to understand our trip through Vietnam until the end, But here we go. We're starting off with this. The norm of a plus b squared. The norm of a plus b squared. And you're like, Dr. Warren, you got to be kidding me. You want to show the triangle inequality, and you're going to start with a square? Give me a chance. This is equal to a plus b dot a plus b. True or false? True or false? True or false? True or false? What did you guys show a dot a was equal to? What did you show a dot a was the same as? For any vector, what did you show a dot a was the same as?
The norm squared.
The norm of a squared. It's one of our most useful results. Is a vector plus a vector is vector? Is a vector plus a vector a vector? Is a vector plus a vector a vector? Yeah, so we're really using, now I'm going to say this as I write it down. In a proof we make the justifications by the property of the dot product, by the property of the dot product, that a dot a is equal to the norm of a squared. We're just stating the theorem that we proved. The a is the a plus b. Okay, this next move, I'm going to write down the justification, and you guys are going to write down the logic. I'm going to write down the justification for the step, and you guys are going to write down the logic. My justification is by the property of the dot product, and these are the two properties that we're using, the distributive property of dot products and my commutative property of dot products. I'll let you get away with being just this lazy next Wednesday. I'll let you get away with just this lazy. This stands for what? This stands for what? Distributive. This stands for commutative of our dot product. Now you guys try to think what the line of logic is going to be to write down here if you're going to use the distributive property first and then use the commutative property later. Write down what you think. You guys write down what you think, then that line of logic will be. If it's going to rely first on the distributive property and then on the commutative property. Okay, for sake of time, if you distributed this twice, what's one of the terms you would have? If you distributed twice and you got your dot product here, what would be one of the terms you would have?
A dot A.
You'd have the A dot A. And then how about if you look at, it's kind of like foiling, except it's a dot product of vectors. The last term would be A plus B dot B. And the middle term would be, well, you'd get a B dot A, and you'd also get an A dot B, but does B dot A equal A dot B for the dot product? Does B dot A equal A dot B? By my commutative properties, so how many A dot B's would you have? How many A dot B's would you have?
2.
2. So then we would have 2 A dot B's. And so what I've done, to explain my logic, I've used the commutative property and the distributive property. Or foiling with the dot product. Okay, now I'm going to again write down the justification. I'm going to write down the justification and you guys are going to write down the logic. My justification is going to be this. By the property of the dot product, that any vector dotted with itself is the norm of that vector squared. That any vector, that A dot A is equal to the norm of A squared. This is my justification and my proof. You guys write down what you think the next line of logic is going to be. You write down from the line above what you think the next line of logic is going to be. And while you do that, I'm going to ask you a question. Is this size reading? Is this size I'm writing reading? Are you able to read that better than my normal writing?
Yes.
Okay, so I'll try to keep writing about that big. I'll just have to keep erasing more. Okay, hold up to the screen what you have. If you have something, hold it up. Let me see what you've got. Guys. Oh yeah. I'm really liking what Rhett has. There. And some of your other ones. Okay, good. I'm seeing some good things. A dot A is the same thing as the norm of A squared. So let's put that in there. Leaving the middle term alone. I don't know what to do with that right now. Okay, I really think if I would have started somebody off with this, just with that side there, after 15 minutes, somebody might have tried this. And then I really think once they were there, they'd probably be able to bounce into this. And then another 5 minutes later, they'd be like, oh, well, look, this is the same. I already know this. It's at this point of the argument next Wednesday where the wheels will fall off. I think you guys could start with this and get to here. It's at this point where I think the wheels are going to fall off. And so this is where I want to be very careful. My next equality is going to be right here. This is the trick. So write that down beside that equality, because when you're studying for the quest, you're going to be like, what did he do to go from there to there? So write down, this is the trick. This is equal to the norm of A squared plus 2A dot B Now, use the result that we got from the law of cosines. That's the trick. Replace that A dot B with the result that we have from the law of cosines. Do that right now. Replace that A dot B with that result that we have from the law of cosines. Replace that middle term. And that's really the trick that you're going to need if you're asked to reproduce this next Wednesday. So what can I substitute in here, guys? What can I substitute for the A dot B? What can I substitute for the A dot B? The
A times one B.
times the
Cosine of theta.
Cosine.
times the cosine of theta. And I don't think, I think it would have taken people quite a while to get to that point. Okay, now draw a unit circle. Draw a unit circle, because I need you to understand this. Draw a unit circle. This is not going to be in my proof. This is just some scrap work that I'm doing. For the dot product, this angle theta, the farthest we're going to let it go counterclockwise is to pi. The largest it's going to get is pi. The smallest we're going to let it go from 0 is minus pi. So theta is always going to be between minus pi and pi. Now you're on the unit circle. What's the biggest value cosine can be if you're going between minus pi and pi? What's the largest value cosine can get if you're going between minus pi and pi? Think of the x-coordinate. What's the biggest x-coordinate on the unit circle? 1. This point over here, where you're 1, 0. It's always less than that. The biggest it can be is 1. What's the smallest it can be? What's the smallest it can be? Negative 1. And that's what we're relying on here, is that cosine of theta is always going to be between 1 and negative 1. And this is going to be my justification. Cosine's always greater than or equal to negative 1 and less than or equal to 1. And so this unit circle is not part of my proof. Okay, come back over to here. I know you're punch drunk. What's this result called again? What's this result we're proving called again? What's it called? The triangle inequality. This is when the inequality comes. It's called the triangle inequality. This is always less than or equal to. This is always less than or equal to. This is always less than or equal to when we put in the biggest number. The largest it can be the largest cosine of theta can be is 1. So this is always going to be less than, this line will always be less than or equal to this line. The only time it's going to be equal is when theta is 0. The only time it's going to be equal is when theta is 0. Most of the time it's going to be less than or equal to. And this is very different than what happens in one dimension. When you have the absolute value of A plus B, a lot of times it's equal to the absolute value of A plus B. Sometimes it's not. But in higher dimensions, it's almost never equal. Just when the angle is 0. Okay, this next part is not part of the proof. You don't even need to write it down. I just got to ask. If you saw an expression, apple squared plus 2 apple banana plus banana squared, could you factor it? If you saw an expression, apple squared plus 2 apple banana plus banana squared, could you factor it? Could you factor this into 2 binomials? And what would they factor into? Oh, anyone? Apple plus banana times the same thing. Apple plus banana. Now, just FOIL it out. What's apple times apple? What's apple times apple? Quickly, what's apple times apple?
Apple squared.
Banana times banana.
Banana square.
When you FOIL, you get two of the same things. This is clearly not going to be in our proof. But look, guys, we've got an apple squared, we got a 2 apple banana, and we got a banana squared. Using algebra, by algebra of the real numbers, because now these are scalars, by algebra of the real numbers, this is the same thing as what squared? This is the same thing as what squared? By the algebra of the real numbers, that's the same thing as what squared? Write it down. Okay, what do you have in here? You better have it right. What do you have in here? What do you guys have? I'll keep asking.
Plus the norm.
Norm of A plus the norm of B squared. Okay, let's take the helicopter out of Vietnam. Now we're looking. We started here. How many people understand that move? How many people understand that move? How many people are good with that? How many people are good with that? Yes or no?
Yes.
Yep.
Yes.
How about from here to here? Are you pretty good with that?
Yes.
Yes.
How about from here to here? How about from here to here? Are you pretty good with that? Was that a yes? Was that a yes?
Yes.
Then comes the
Trick.
where we use our law of cosines identity. Then comes another trick. This is really trick 1, and this is really trick 2. The biggest cosine can ever get is 1. So this is when the inequality comes in. This is just factoring. The norm makes it look far harder, but it's just factoring. Okay. If A is equal to B, which is equal to C, which is equal to D, which is equal to E, which is less than F, which is equal to G, what must logically follow? Dr. Warren, I wasn't focused. If A is equal to B, which is equal to C, which is equal to D, which is equal to E,
A is equal to
which is equal to F, which is which is yes. There's no saving that. What must logically follow is that the norm of A plus B squared, where I started, is less than or equal to the norm of A plus the norm of B squared. You're like, Dr. Warren, those are the same things. No, they're not. They're very different. Here, this is the vector. Here, we're adding the norm of 2 vectors and squaring it. Oh, gosh, I'm running out of board space. Guys, I got to rate. It's part of the proof. Draw the square root function. What the hell did you say, Dr. Warren? Draw the square root of x. What does f of x equal the square root of x look like? Draw the square root of x. Make your high school teachers proud. If f of x is equal to the square root of x, what does that function look like? What does that function look like? What does that function look like? Draw the square root. Okay, now hold up your paper. I want to see somebody's paper. I want to see what you have. I want to see what your square root. Yeah, baby, that's awesome. So this is the square root function. This is the square root function. Okay, now mark two values on your x-axis. Mark 2 values on your x-axis. Okay, I went way too small. I went way too small because I'm sure it's going to be blurry. But here what I want you to do is I want you to put the norm of the vector A plus B squared. It's the smaller quantity. And over here, I want you to put the norm of A plus the norm of B squared. So the first thing, that first dot is the norm of A plus B squared. The next dot is the norm of A plus the norm of B squared. Did we not show that this was less than this? Did we just not show that? Did we not just prove that? That this is less than this? Because the square root function's increasing, then the square root of the norm of A plus the norm of B squared has got to be less than the square root of the norm of A plus the norm of B squared. But the square root of something squared is, essentially the absolute value, but we're positive, is just itself. So by algebra, I can take the square root of both sides. You're like, Dr. Warren, why the hell are you caring? Look at me, guys. You got to be super careful with inequalities. You got to be really careful with inequalities. When you take the inverse of something, sometimes the sign switches, and it can burn you if you're talking about building bridges. You take the inverse of both sides, sometimes that inequality switches. But because the square root's increasing, if the inverse function's increasing, then you know it's not going to switch. If it's decreasing, it is going to switch. So our last step, and again, because it's COVID, I'm going to let you get away with algebra of the reals. You do not have to justify over here what I just did. That was only for you. Then the norm of A plus B is less than or equal to the norm of A plus the norm of B.
For the logic on trick 1, could we just write the law of cosine?
It's a little bit more than the law of cosines because it's a vector identity.
Okay.
So you better put it in there because somebody would punish me if I let you get away with that. Okay, so I better be a little bit more careful. Are we done? Are we done with the proof? Did we prove the triangle inequality? Did we prove what we wanted to show?
Yeah.
Was it a little bit more involved than duh? Okay. Okay. I've got 5 minutes. I guess I'll do this. I'll end with this. On Monday, we're going to start the cross product. It's our last vector product we need to define. Okay. Draw any two vectors. With their butts together. And I'm just going to hold up mine. Mine are in 3-dimensional space. Yours are in 2-dimensional space. Mine are in 3-dimensional. This is when I don't like this wide angle lens. Okay, look at your vectors. Is the dot product of the two vectors you just drew positive or negative? Now, Dr. Warren, there's no damn numbers. Is the dot product of the two vectors you just drew positive or negative? And you're like, whoa, seriously, Dr. Warren? Seriously? You expect me to answer this? Do I look like David Blaine? That I'm going to pull this out of the air? Well, A dot B using the law of cosines is equal to what? A dot B using the law of cosines is equal to what? Help me out, help me out.
Of A times the norm of B times cosine theta.
The norm of A is positive. Agree or disagree? The norm of A is positive. Agree or disagree? Norm of A, positive.
Agree.
Norm of B, positive. So the entire sine is determined by the cosine of the angle between them. Now, think about your unit circle. Think about your unit circle. Here's minus pi, and here's pi. In which quadrants would cosine be positive? In which quadrants would cosine be positive?
1 and 4.
In 1 and 4. I know cosine, anytime I have an angle, the x-coordinate is going to be positive if I'm here or there. But what if I have an angle like that? What if I've got an angle like that? Would cosine be positive or negative? Would cosine be positive or negative? I'll keep asking. Will cosine be positive or negative?
Negative.
Negative. Similarly, if I've got an angle like this, it's going to be negative. So this is fun. As long as the angle between them is less than 90 degrees, as long as it's acute little angle, as long as it's less than 90 degrees, the dot product will always be positive. But if it's obtuse, if it goes bigger than 90 degrees in any direction in three-dimensional space, then it's going to have what sign? Then it's going to have what sign?
Negative.
Negative. Okay, so if the dot product is positive, you know that it's less than 90 degrees. If the dot product is negative, you know your two vectors are sitting in three-dimensional space where the angle between them is bigger than 90 degrees. And that's really useful. That's really useful. So that's what we're going to end class with. We're going to end class with this. If A dot B is positive, then I know my two vectors, the angle between them, the absolute value of theta is less than 90 degrees or pi over 2. I'll do math. If A dot B is negative, then I know my angle is bigger than pi over 2. What if it is pi over 2? What if it actually is pi over 2? What if it is pi over 2? What's the dot product? What if it is pi over 2? What's the dot product?
0.
0. 0. Is this making sense, guys? Is this beginning to register with you guys? Are you beginning to kind of... I know it's like surfing. Guys, I know it's like surfing. I remember when I thought I was drowning most of the time. It's like surfing, but you'll get better with it as long as you get up and when you're bored. Look, it's going to hurt. It's going to hurt. When you learn to surf, it hurts. It hurts. When you learn to skateboard, does it hurt? When you learn to skateboard, does it hurt? Yes. Anything fun hurts in the beginning. If it's going to be fun, it's going to hurt. Okay. Stay up on your boards. Stay up on your boards. You have what next Wednesday? You have what next Wednesday? Quest 1. What was due today?
Homework.
Homework. That WebAssign homework. Okay. I will see you on Monday. Guys, have a safe weekend. Have a safe weekend. Okay. Stay healthy. Stay healthy. Thank you. Thanks, guys.
Good weekend.
Dr. Warren.
Yeah. Who's this?
It's Luke.
Luke, how are you doing?
Doing well. How are you?
Good.
I just had a quick question. I take all my notes on an iPad. I've already told you this. I don't really remember, but would it be possible if I took the written portion?
Oh yeah, I greatly prefer that. Just because it looks like you're doing the test and turning that in. So that would be awesome, Luke.
Okay, cool. Just wanted to make sure.
No, that's perfect. That's perfect.
All right, great. Thank you so much.
All right, thanks.
All right,
Have a good weekend.
Thank you.
Cool stuff, cool stuff.
Oh, thanks, Michael. Thanks.
Is this similar to a limit cycle at all?
Excuse me?
Is this similar to a limit cycle at all?
Oh, it is very similar, but we'll get into stuff like that a little later on. Right now, we're just kind of like trying to lay in the geometry.
The pieces on, yeah, figure out everything is.
Yeah, once we do that, once we can have that, then we can start really doing some fun things.
No, yeah, you got some cool apples. I like the circle, the little, yeah.
Awesome, awesome. What's your major, Michael?
Right now it's math actually.
Oh, okay, awesome. What year are you?
Junior.
Okay, now have you been at JMU the whole time?
Yeah.
Okay. That's, well, who's your advisor?
Con.
Okay, well, you can come to me too, okay? If you have questions as far as like what to do. Because it sounds like you kind of like a lot of some of the applications.
Oh yeah, no, that's like all I do.
Okay, all right. I'm an applied mathematician, so I that's what I enjoy too.
Oh, wow, that's fantastic, awesome. Yeah, I guess I'll, yeah, cool stuff with that. Cool
All
stuff.
right, thanks, Michael.
All right, man, I'll catch you
Monday.
Monday, yep.
They're so fun.